Good afternoon, and thank you for joining us for Biodiesel Magazine's webinar on how methanesulfonic acid, or MSA, can improve your industrial biodiesel and ethanol operations. Today's webinar is sponsored by BASF. My name is Ron Cutterba. I'm the editor of Biodiesel Magazine, and we're happy to have you all with us this afternoon. Over the past decade, the ability to process lower cost, lower quality feedstock has become paramount for many biodiesel operations to remain competitive. While there are several ways for biodiesel producers to process these lower cost, lower quality feedstocks, many choose to esterify free fatty acids, which involves using harsh chemicals such as sulfuric or other acids that are corrosive, hazardous, can form emulsifier byproducts that increase separation times and add unwanted color to biodiesel. As a biodiesel producer, even if you are not esterifying FFAs, chances are you're still using acids in other parts of your process, such as neutralization of crude biodiesel to remove base catalysts and salts, or neutralization of glycerin and soap splitting to separate fatty acids. And for ethanol producers who use acids in oil extraction or CIP systems or other areas of the process, there are often unwanted side effects as well. Today we have a panel of experts lined up and prepared to discuss how your operation can benefit from switching from your current acid or acids to BASF's Lutropur brand of MSA in 70% concentration and its new MSA XP product in 94% concentration. A quick note before we begin with the presentations. If you have a question for our speakers, feel free to type it into the panel on the right side of your screen. After all of the presentations, we will get to as many questions as possible during our Q&A session. If your inquiry is for a specific speaker, please indicate that in your question. Also, if you could, please type your question in a manner in which it will be easily read, meaning avoid abbreviations, any obscure acronyms, or incomplete sentences. Also, during the Q&A session, we're going to have another expert from BASF who's not speaking on the panel, Joseph Borst. He's a senior technical service representative with BASF, so he'll be standing by and ready to help answer any technical questions once we get to the Q&A session. At this time, before we begin with our presentations, we'd like to pause for a commercial break from today's sponsor, BASF.
BASF's Care Chemicals division offers a broad range of ingredients for the personal care, hygiene, home care, and industrial and institutional cleaning industries, as well as for technical applications. We are the global leading supplier for the cosmetics industry, as well as the detergents and cleaners industry, and support our customers with innovative and sustainable products, solutions, and concepts. The division's high-performance product portfolio includes surfactants, emulsifiers, polymers, emollients, chelating agents, cosmetic active ingredients, and UV filters. Super absorbent polymers developed for the full spectrum of hygiene applications complete the range. We have production and development sites in all regions and are expanding our presence in emerging markets. Further information is available on the internet at www.care-chemicals.basf.com.
I'm pleased to welcome our first speaker, Benjamin Plants, BASF's new business development specialist in formulation technologies. Benjamin, welcome to the broadcast, and thanks for being with us today.
Thank you very much, Ron. Hi, everybody. My name is Ben Plants, and as Ron said, I'm a new business development specialist at BASF with a focus on the biodiesel industry. Today, I'm excited to introduce you to our new product, Lutropur MSA XP. While my presentation will focus on Lutropur MSA XP, I realize that some of you may not be familiar with the original Lutropur MSA. Lutropur MSA is the simplest organic sulfonic acid and has an active content of 70%. Our Lutropur MSA is produced in Germany using an eco-friendly process, and we introduced this product to the biodiesel industry in 2013 as an alternative to sulfuric acid. Lutropur MSA has many properties that make it a good alternative to sulfuric acid in multiple steps of the biodiesel process. Like sulfuric acid, MSA is a strong acid with the power to convert free fatty acids into biodiesel through esterification. Unlike sulfuric acid, MSA is a non-oxidizing acid which prevents the production of undesired side products during its use in the biodiesel process. And finally, sulfuric acid MSA is much safer and easier to handle than sulfuric acid. While Lutropur MSA can be used in multiple steps of the biodiesel process, including pretreatment, degumming, and neutralization, we have seen the largest demand of MSA for its use in pretreatment. The problem, however, is that the esterification of free fatty acids to biodiesel is an equilibrium reaction that produces water. The end result here is that the more water you put into the reaction, the lower free fatty acid conversion you will achieve. Thus, the name of the game is to decrease water content. In addition to lower water content, however, biodiesel producers also need an esterification acid to have a low melting point and be safe to use. Before the development of Lutropur MSA XP, BASF already supplied 2 MSA products to the biodiesel industry. The original product, Lutropur MSA, with an active content of 70%, and Lutropur MSA 100 with an active content of 100%. While each product excels in certain applications, for esterification of free fatty acids, we wanted to introduce a product that took the low corrosion benefit of the Lutropur MSA and combined it with the high conversion benefit of the Lutropur MSA 100. After researching different activity levels, we determined that 94% was the magic number, and Lutropur MSA XP was born. This product marries the benefits of the previous Lutropur MSA offerings, resulting in a more efficient esterification catalyst. While we typically compare our MSA products to sulfuric acid, Lutropur MSA XP shows proven advantages over the other available grades of MSA. These major benefits can be seen in free fatty acid conversion, improved handling, and lower corrosion. In this graph, Lutropur MSA, the 70% active version, is represented by the light green line, and the Lutropur MSA XP, the 94% active content version, is represented by the dark green line. You can see that in less than 20 minutes, the Lutropur MSA XP treated feedstock reaches a lower free fatty acid content than the Lutropur MSA treated feedstock. Also, you will notice that the original free fatty acid content was actually higher for the Lutropur MSA treated feedstock than for the Lutropur MSA XP treated feedstock. So if they had actually been equal, the increased conversion picture here would look even better than it already does. In another experiment, we were able to show that after 2 hours, Lutropur MSA XP achieves a 3% increase in free fatty acid conversion compared to 70% active MSA. It is also interesting to note that the Lutropur MSA XP actually performed better than the Lutropur MSA 100 in this experiment. While I realize that many of you aren't using a 50% free fatty acid feedstock, the take-home message here is that the Lutropur MSA XP provides an overall more complete conversion than other grades of MSA. Another benefit of Lutropur MSA XP is that it is easier to handle than Lutropur MSA 100. As you can see from the table, Lutropur MSA XP freezes at 10 degrees Fahrenheit. This is lower than the freezing point of both Lutropur MSA 100 and 98% active sulfuric acid. As a result, any producer currently using Lutropur MSA 100 or 98% active sulfuric acid shouldn't have any freezing issues by switching to MSA XP. On the flip side, you can see that Lutropur MSA and 96% sulfuric acid have lower freezing points than the Lutropur MSA XP. This difference could mean that outdoor operations in the northern United States and Canada may not be able to use Lutropur MSA XP. However, based on the average winter temperatures of some selected states, much of the biodiesel production industry falls into a geography where MSA XP can be used without freezing problems. The final benefit of Lutropur MSA XP that I would like to discuss is its corrosion resistance benefits versus other MSA grades. These tests were conducted with our MSA products as is on multiple grades of steel for 14 days at 140 degrees Fahrenheit. You can see that for all 3 grades of steel, the Lutropur MSA XP showed negligible corrosion. Also, as I mentioned before, when discussing corrosion, we typically compare our MSA to sulfuric acid. While I didn't actually include the corrosion rates of sulfuric acid in this table, you can rest assured that the sulfuric acid would have shown significantly more corrosion than any of these Lutropur MSA grades in this test. We also conducted corrosion experiments at biodiesel reaction conditions, and we found the same results. Compared to Lutropur MSA XP shows significantly reduced corrosion on both 316L and 304 stainless steel. As I've shown you, Lutropur MSA XP is a more effective and safer free fatty acid esterification catalyst than both sulfuric acid and other grades of MSA. In addition to safety, I've also demonstrated that Lutropur MSA XP provides better corrosion resistance than the alternative. Combine that with the increased esterification performance, and we believe the Lutropur MSA XP is the best all-around esterification acid for your biodiesel process. So you may be asking how you can get your hands on some Lutropur MSA XP, and the good news is that it's already available. This material is produced in Germany, the same as our other grades of MSA, and will require an 8 to 10 week lead time. We currently offer Lutropur MSA XP in 1,200 kilogram totes. However, based on business needs, we can potentially offer alternative package sizes. Samples are already available, and if you're interested in learning more or obtaining a sample, please don't hesitate to contact me. Thank you, and I'll hand it back to Ron.
Hey, thank you very much, Benjamin. Nice job. Before we move to our next panelist, who will discuss Lutropur MSA's benefits to ethanol production, I wanted to provide our audience with some feedback on MSA usage from one of the nation's leading biodiesel producers, World Energy. While a representative from World Energy was unable to join us today, they were kind enough to provide some feedback for us on their usage of MSA. World Energy tells us that they initially switched to MSA in its biodiesel operations 2 to 3 years ago, specifically to minimize corrosion. In addition to using acids for esterification, World Energy also uses acids for neutralizations, like many biodiesel producers do. And World Energy tells us that they did, in fact, experience less corrosion with MSA, and that they found MSA to be safer than sulfuric acid. Regarding BASF's Lutropur MSA XP, World Energy tells us that they do anticipate a reaction improvement with the 94% MSA XP versus the 70% concentration MSA product, and they are certainly willing to try it out for comparison. Finally, when asked what they would tell other biodiesel producers who are considering switching from sulfuric or other acids to MSA, World Energy said that they would, in fact, recommend trying it out. So I want to thank the folks at World Energy for providing us with some of their feedback on their use of MSA. At this time, we're going to pause for another word from our sponsor, BASF.
Lutropur MSA is an ideal acid for all ethanol plant requirements. Its ability to effectively remove scale makes it an excellent acid for CIP solutions, replacing sulfamic, and other acids for this application, and even caustic. In addition, by partially replacing sulfuric acid to acidify the process, Lutropur MSA can reduce fouling, increase corn oil recovery, and improve DDGS color. Lutropur MSA from BASF is improving ethanol plant efficiency.
Our next speaker this afternoon is Tony Newton. Tony is a field technical support leader at BASF. Tony, it's a pleasure to have you with us here today.
Thank you, and thanks everybody for joining the presentation. Before I get started, I just wanted to give a quick overview of the business unit that I'm in. It's BASF Enzymes, LLC, and we are actually headquartered in San Diego, California. We're a world leader in high-performance enzymes, mainly because of our unique enzyme discovery and evolution technology platform. We do manufacture our enzymes in Mexico City, and the markets that we're in include human nutrition, grain processing, animal health and nutrition, detergents and personal care, and oil and gas. And BASF Enzymes LLC is also the market-facing unit for BASF to the fuel ethanol industry. And so that would include enzymes and chemicals. And today we're really going to be talking to you about 70% Lutropur MSA, which is one of our chemical offerings that we're excited about. Next slide. Okay, so we rolled out MSA to the ethanol industry in late 2015 as mainly a sulfamic acid replacement. Since then, we've found a lot of different applications for MSA in the ethanol industry, and today we're going to go over some of those applications with you and the data that we've gotten since late 2015. So this is just a quick recap and reminder that really for the ethanol industry, we're going to be talking about 70% MSA because that's the one that's the best application for fuel ethanol. And we just want to do a quick recap on the properties of MSA and why we think these are important to the ethanol industry. It is a strong acid, very similar to sulfuric acid in strength. It is non-oxidizing, which we think is going to give it a lot of benefits as far as DDGS hunter color score and corn oil extraction. It has very high solubility of its salts. As I said, and as John Brazier, one of our customers, is going to talk about later, we think it does offer advantages in corn oil extraction system applications. With MSA, there's no VOC, low TOC, and it's odorless. So in contrast to nitric acid blends that are currently on the market, it will be much safer for operators to handle. It's easy to handle because it's in liquid form. So if you use MSA in place of sulfamic acid, the operators are not going to have to deal with and dump 50-pound bags, and also deal with the dust and things that come along with a dry acid. 70% MSA and all MSA grades have a very high thermal stability. So that means when you're using them in a CIP system, you can really heat up your CIP solution and not worry about it, MSA breaking down like sulfamic acid is going to do. And it's readily biodegradable. So here's a comparison of acid strength using equilibrium constants. You can see on the far left, acetic acid is a very weak acid, and you can follow the bar graph up looking at formic, citric, phosphoric, and then sulfamic, and then you can see the acid strength really jumps up when you go to MSA, sulfuric, and hydrochloric. So MSA is almost double the acid strength as sulfamic and very similar to sulfuric acid in strength. Here's a example of how Lutropur MSA shows minimal oxidation on sugars. So no matter how good your fermentation is, in the back end when the streams get concentrated at the ethanol plants, you are going to have some residual sugar left. In this experiment, experiment, we added Lutropur MSA to table sugar versus sulfuric acid. So you can see after 60 seconds what the reaction looks like, and after 90 seconds what the reaction looks like. And the sulfuric acid is really oxidizing any residual sugars left that you have in your process. So that's what's going to contribute to darker Hunter color scores throughout your system and in the DDGS. Also, this reaction here tends to create emulsifiers, which would inhibit corn oil extraction. This is a graph of the solubility of methanesulfonic acid salts compared to chloride and sulfate salts. So in the middle of this graph is 0 grams per liter concentration, and on the outside is 1200. And you can see that the methanesulfonic acid salts right around the outside edge or towards the middle of this graph versus sulfate salts. So what that means is that MSA is going to be a lot more efficient at removing scale from your system than sulfuric acid would in CIP applications and in continuous addition applications, such as beer column feed acidification. Here's another example of how well MSA removes calcium oxalate scale. So in this experiment, we took calcium oxalate solids and added them to water in a beaker. And then we measured the transmission rate through that beaker, so measurement of light through the beaker, as we titrated with methanesulfonic acid versus sulfamic acid. And you can see, based on the curve, that the MSA reacts with calcium oxalate more readily than sulfamic. So it's going to do a much better job at removing calcium oxalate fouling. And we actually had a customer that started up an older ethanol plant and had calcium oxalate fouling in their fermenters, and was able to remove all of that with MSA pretty easily. Here's an example of calcium carbonate removal with MSA. We just took calcium carbonate tiles and treated them with MSA versus sulfamic acid. And you can see that the MSA performs about 30% better than sulfamic acid on calcium carbonate fouling. So calcium carbonate, or oxalate and carbonate, are two types of fouling we see in the ethanol industry. Here's an example of MSA really, it is dissolving some of the fouling that we see on evaporator tubes and other pieces of equipment in the ethanol industry, but it also seems to get between the fouling layer and the metal of the piece of equipment. So a lot of times what we see is big chunks of inorganic and actual organic fouling sloughing off of different pieces of equipment when we CIP with MSA. And we think that's because the organic and inorganic fouling is kind of mixed together or layered. And once the MSA starts working on the inorganic fouling and loosening up that system, that we get large chunks of material coming off. And we'll look at some examples of that in the next few slides. Here's an example of, we did some testing on beer that was unacidified from an actual ethanol plant. So we got some samples from I believe a Delta T plant, and we acidified the beer with sulfuric acid versus MSA down to 3.6 pH, I believe, and just to see what kind of oil layer we could get. And you can see from the pictures that there's a much larger oil layer when we acidified with Lutropur MSA. So this laboratory test is what led us to do other experiments in the actual ethanol production plants on corn oil extraction applications. And lastly, just an example of corrosion. So we're looking at MSA versus sulfuric acid. You can see that MSA is much less corrosive on stainless steel, especially at the higher temperatures. So the original coupon is in the middle, and you can see at the higher temperatures the MSA is slightly discoloring the coupon, but really no metal degradation, versus the sulfuric acid, which is really starting to eat away some of the metal. So what that means is some customers do have a lot of sulfuric acid usage in their plants, and that seems to all get concentrated in the dryer, and where you can see some metal degradation. So using MSA to replace some continuously added sulfuric acid could potentially extend equipment life. So just a recap of the advantages. It is a strong acid. Its salts are extremely soluble. We see a high degree of scale detachment. So those three first bullet points mean it's going to be a very good CIP cleaner. We think it's well suited for corn oil extraction systems. We'll show you more examples of that in a little bit. It's non-oxidizing, so we think that again is going to help your corn oil extraction system yields and potentially hunter color scores. It's stable to hydrolysis and high temperature. And the reason we put that in there is because that's very different from sulfamic acid. As soon as you liquefy sulfamic acid in your acid CIP system, it's going to start breaking down and become ineffective even before you pump it out to the piece of equipment you're CIPing. There are some synergies with other chemicals. So because MSA is non-reactive, theoretically you could actually mix other acids and surfactants and different chemicals with it. It's less corrosive than other strong acids, odorless and clear, and has a low viscosity and vapor pressure, which all are going to make it much safer than, say, a nitric acid blend that you may have been using. And it's readily biodegradable, and it is GRAS approved for these applications. So the first application we really rolled MSA out for was acid CIP applications, primarily in ICM plants. And I say ICM because ICM plants already have the stainless steel equipment and acid CIP systems that are needed to clean the beer mash exchangers, evaporators, and other pieces of equipment. So when we first started replacing sulfamic acid with MSA, the things we noticed on evaporator efficiencies were we were actually able to measure improved condensate flow per pound of steam input. So that's a metric that we look at when we do an MSA CIP trial, and we do see better, basically, evaporator efficiency by more condensate coming out of the system per pound of steam input. Oftentimes when we get the scale off of the evaporators, there's an increase in throughput through the system, so an increased flow of thin stillage and syrup. And for those of you that are feeding your corn oil extraction systems, kind of in the middle of your evaporator system, that has actually helped some plants to debottleneck that process too. And then lower system pressures on the shell side and lower steam usage. A lot of plants are using Lutropur MSA for the beer mash exchanger CIPs, and we were able to measure higher heat transfer, longer online time. What almost all the plants notice when they switch from sulfamic to Lutropur MSA is the CIP batches do not have to be built nearly as much. So a lot of plants go from building a CIP batch once a week to twice a week, for instance. We have also had one plant that was acidifying their beer feed with sulfuric acid in order to keep their beer mash exchangers clean. And once we applied Lutropur MSA to the beer mash exchanger CIP, they were able to eliminate the continuous acid dose to their beer column. And then a lot of our customers are using MSA to clean their corn oil extraction centrifuges and the stack coil off the boiler/thermal oxidizer at ICM plants. So every plant that has tried MSA in this application has converted to it full time. So for this specific application, we have a 100% conversion rate. So now we'll start to look at the actual applications and examples. This is a 40 million gallon per year ICM that we cleaned. I believe these pictures are for evaporator number 7. So you can see the rinse before MSA when they just rinse the evaporator out. You can see after 1 hour of MSA CIP, and the plant manager was really amazed on how dark this was, because this was the middle of November 2015, and they had just water blasted their evaporators in September of 2015. So we were under the impression they were pretty clean when we were doing the CIP. There's a rinse afterwards, and then they did do a 2-hour caustic cleaning. And this is some of the material that we got out. It's we think it's pretty old material because of the color. And you can see that the different colors in there we think indicate inorganic and organic fouling breaking off the tube wall. Here's some data from that evaporator system. We got about 50 days of baseline. This is thin stillage flow to the evapes, and we just divide it by daily grind to correct for basically the plant production rate. As we cleaned evap 7 and other evaps, the plant pretty much debottlenecked their evaporator system, was able to get much more throughput. This is the second effect shell side pressure, dropped immediately and stayed low, and also as we cleaned more evaporators. And I think, you know, got to more of a maintenance CIP instead of getting a lot of material off every time. We were more to a maintenance CIP where we're keeping the evaporators clean. The shell side pressure stayed low. We just recently cleaned the second effect evaporator at a 55 million gallon per year delta T. So if you work at a delta T, you know usually the second effect is the problem child of the evaporators. This is the scale that we got out after cleaning with a 5% MSA solution at 180 degrees Fahrenheit. And there was quite a bit of this that was coming off, and the plant personnel were surprised and happy to see this. Because the delta T didn't have a stainless steel CIP system, we just took the tote out to DD&E and pumped it into the evaporator suction side of the evaporator recirc pump. So we're able to measure condensate flow from this system afterwards, and the data is very limited at this point. We actually just did this. But the condensate flow jumped up right away, and the plant manager made the comment that he hadn't seen this type of performance since the plant was started up and all the systems were squeaky clean. This is second effect differential pressure, so shell side pressure minus tube side pressure on your second effect at a delta T, and this is you can see a very large drop in that pressure. This is at the same production rates. Here's where we're starting the system back up, and then you see it come to equilibrium. So another application we actually have is we do have 2 plants that have replaced all caustic usage in their fermenter CIP with MSA, and we do see lower infection rates, lower antibiotic usage for these 2 plants that we're looking at, lower fermentation sodium levels. They don't have to deal with the foaming of the CIP anymore because they're not using caustic, and the MSA is not going to foam. We do have data from a whole year of doing this, and we've estimated that the total cost of CIP per gallon of ethanol produced is around $0.0006 per gallon. And we know that for traditional ICM plants, it's about 10 times that if you're using a non-MSA acid such as sulfamic and a caustic CIP program at your fermentation. We think the savings for a 50 million gallon per year plant is around $270,000 a year. However, there is a capital investment required. Normally, the plants do not have stainless steel systems, CIP systems, going to their fermenter spray balls and fermenter heat exchangers. These 2 plants happen to already have that. We do think that if a plant did invest to go over to an acid CIP program for fermentation, it would most likely be less than a year payback. This is just one piece of data. This is drop data for lactic acid, and we have a baseline here where they were already using sulfamic acid for this plant, and when they switched to MSA, we basically maintain the same average lactic acid value, but have tighter control limits. I will say that this also included a 20% reduction in antibiotic usage. The other plant we have did go from caustic to Lutropur MSA, and we're waiting to get data from that. So the last application that I'm going to talk to you about before John starts is we do have a plant right now, a 55 million gallon per year Delta T that has very low hunter color scores. So because MSA is non-oxidizing, we decided to try to acidify the beer with MSA partially. So they were using about 2,400 milliliters a minute of sulfuric acid to acidify their beer feed stream with a target of 3.6 pH. We came in and put on 625 mils a minute of MSA, and also added our fueltase phytase to the fermentation. So with that combination, we were able to increase the beer feed pH up to 4.0 without seeing any fouling of the reboiler, which was their fouling bottleneck. So that resulted in significantly less sulfuric acid usage. We're still collecting hunter color score data, but it does look like the hunter color scores came up. We noticed almost immediately about a 14% increase in corn oil extraction yield. And the other things that we're going to be looking at is we're wondering if the overall reduction in acid at the plant is going to result in some lower corrosion inhibitor usage at the ethanol final product. So these results are pending. This trial is ongoing, and we're excited about it. We're at 4.0 beer feed pH, and we're hoping that we'll be able to get up to the target of 4.3. So just to recap, performance-wise, Lutropur MSA is going to be superior to most of the acids out there that are being used in the ethanol plants. It's definitely going to be safer than the other acids that are currently being used. And it is eco-friendly and biodegradable. So we do think it's a good choice for the ethanol industry. And for more information, you can contact Brian Hoskins. He's our product manager for BASF grain processing. Thank you.
Hey, thanks, Tony. Wonderful job. Fascinating presentation, packed full of data. We appreciate you being here. Just a reminder to the audience, if you have a question, and we've already been receiving several questions, we appreciate those, and we'll get to those in a bit. Please type it into the panel on the right side of your screen, and we'll attempt to get to as many as possible after the presentations. I'd like to welcome our final panelist today, John Brasher. John is the Senior Process Engineer with Ergon Biofuels. Ergon Biofuels is a 55 million gallon a year ethanol plant in Mississippi. John's going to discuss his experience using BASF's Lutropur MSA in his operation. John, thanks for being with us today.
Thanks, Ron. So just to give you a little information about Ergon Biofuels, Ergon Biofuels is actually a subsidiary of Ergon Inc. It actually acts as its only biorefinery within Ergon. Ergon actually acts primarily as a sophisticated crude oil processor and a transporter of marketer of refined products. Ergon is a very large company. We have several business segments. Biorefining is one of the newer aspects and items to Ergon's overall portfolio. As Ron mentioned, we're located in Vicksburg, Mississippi. We are a 54.7 million gallon per year nameplate Delta T base design. One of our recent expansions to the initial design of the plant was a front-end oil extraction technology. And our process is a little different than a typical oil extraction. Typically, an oil extraction for an ethanol plant will be placed somewhere in the evaporation train post-distillation, or sometimes a plant will actually attack the syrup directly. Ergon chooses to extract its oil directly from the mash, leaving liquefaction rather than waiting for fermentation to occur. In doing so, there are some major benefits to separating oil prior to fermentation. There are also a few cons. The major benefit being you actually free up a lot of space in fermentation for fermentable solids, so you actually increase your overall ethanol production. You also improve pump and heat exchanger efficiencies, and you also see a reduction in fouling. You actually see an increase in efficiency in your evaporators and your dryers. Couple of the cons. The big one that we find at Ergon is that since it is a non-traditional method, there's not a lot of expertise within the industry, so you do a lot of your own R&D locally. We do, however, see a lot more emulsion on the front end of the process than on the back end, meaning prior to fermentation. We believe that has a lot to do with the protein, oil, water, I guess you can call it a binding event if you want to call it that. Since you don't have fermentation to produce ethanol, you don't see a lot of the extraction that you normally see, or excuse me, separation that you normally see on a back end. So all in all, you have less free oil to separate. So this free oil that you are not able to separate as a result of being prior to fermentation, you have an overall lowered potential yield. So again, here's an easy generalized extraction diagram that we have. Again, we're just saying that we have a separation technology between liquefaction and fermentation to produce a distiller's corn oil. We enlist the use of 2 centrifuges to capture oil. We use a disc stack, which allows for a high amount of flow rate to enter the machine, and we actually produce a crude cut of oil. This crude cut is usually a 10 to 30% mixture of oil and some solids and centrate. This crude cut is then sent to a tricanter, and this tricanter then creates a refined cut of distiller's corn oil. Another benefit that I forgot to mention, typically a front-end oil extraction system will have a lower free fatty acid content than a back-end system. But again, with every pro, there seems to be a con with front-end oil extraction. One of the major cons, again, is emulsion. And again, this emulsion layer seems to be exaggerated in the front end. Ergon has used several polysorbate-based emulsion breakers to try to break this bond. This emulsion breaker, or these emulsion breakers, I should say, are introduced between the disc stack and the tricanter. Reason being is the flow to the tricanter is much smaller than the disc stack, so we can consume less product, and basically to achieve the same effect. Even though we've used these, we have some issues with using the polysorbates. It seems that since most of them are geared towards a back-end process, there are some negative consequences to using the front end, or that's what Ergon has seen anyway, specifically with moisture content. So Ergon has experimented with other methods of breaking emulsions. There are several. You can adjust the temperature, you can adjust the pH, you can adjust the residence time. There are several. To us, the easiest one without a large capital investment would be to adjust the pH. So that's where Lutropur really fits in for us. We've tried various acids and bases in the lab setting. However, these often prove to be economically infeasible, and typically, if they are not economically infeasible, they will actually introduce a health hazard to the facility. So Lutropur being generally much safer, much more operator-friendly, it makes it easier for us to set in place of a traditional polysorbate emulsion breaker. And again, as others have said, it's similar in strength to sulfuric acid, regarding acidity anyway. So going back to lab-based trials, we've tried several doses of Lutropur MSA, and this is at the 70% concentration again. We found that the 1500 ppm was the most economic dosage. And again, our lab setting, we tried our best to mimic the process that we have on the front end of the process. So we treated a crude cut of oil off of this stack centrifuge. So the results at 1500 ppm by volume, we actually reduced the pH from a concentration of about 4.95 to about a 3.7, which results in about a 25% increase in free oil against the standard. And the standard had no emulsion breaker. The other benefit that we did not expect, we expected it to be similar, but actually it was a greater benefit in favor of Lutropur, was that we actually freed more oil, which would equate to about a 0.1 pound per bushel over the competitor polysorbate emulsion breakers. One thing I forgot to mention is after we did these tests, we actually took these samples and set them up on a benchtop fermentation, just to prove that this would not have any ill effect on fermentation. We wouldn't have any problems with yeast. And we actually overdosed it by about 50 times and had 0 issues with fermentation. Again, this was an accident. We miscalculated something, but it was nice to know that, again, even with more than we expected, it did not harm fermentation at that dosage. So we actually took a tote quantity, again, we set it in place of the original emulsion breaker. The results being that we actually dropped the pH from a 5.07 at the start down to a 3.9 pH, so it's a little bit less. But that actually created an increase of 40% of oil that was recovered, and that also similarly had a 40% reduction in the emulsion layer. The samples that you see on the bottom right, that is actually feed to the tricanter. We call it the polisher, so you'll see POL. You can see that emulsion layer has dramatically decreased, and you can see the oil layer increase quite a bit. One additional benefit that primarily is a benefit to our process is we do use sulfuric acid prior to fermentation. So with the use of sulfamic acid, or excuse me, MSA, we were able to reduce the overall amount of sulfuric acid required for fermentation. Other opportunities that we are looking at, as Tony has spoken about, we are looking to in the future replace sulfamic acid. We use a powder. It's really unsafe for our process. So moving forward, we plan to use Lutropur MSA as a source for acid CIP. Again, driving factors for this is safety, economics, and customer expectations. We have to have products that have the GRAS certification. Other ethanol plants have similar expectations from their customers, but safety was the biggest factor for us here. Another one that Tony mentioned is we are looking to have it as a possible supplemental aid to sulfuric acid being added to the beer, which feeds our beer column. Again, our beer column reboiler is a bottleneck to our facility, so we do have to add a large amount of sulfuric acid. And guys, I want to thank you for listening to me today, and I apologize for any misspeakings I may have had, but thank you.
Hey, thanks, John. Nice work and great presentation. We've got some questions for you that have come through. We've got several questions in the queue, so I'm going to go ahead and get started. We've got a good mix of questions regarding ethanol and some other questions regarding biodiesel. So first question is for the ethanol team, and Tony, perhaps you can answer this. What are the animal feed regulations for MSA salts?
Joe, would you want to take this? I mean, I know we do have Lutropur MSA GRAS certified for DDGS, and we'd be happy to send out that GRAS certification to any plant that's interested.
Yeah, I can second that. We have a GRAS opinion, and it is approved for ethanol applications, and all the applications that have been discussed certainly fall under the GRAS level, use level that we've established, which pretty much covers almost any application you could imagine for ethanol production.
Thanks, Tony. Thanks, Joe. Just to remind everybody, Joe is Joseph Borst with BASF. He is helping out with the Q&As for both ethanol and biodiesel questions. For biodiesel questions, we also have, of course, Benjamin Plants, who gave his presentation earlier. We've got a biodiesel question. How would you measure esterification performance in the field? Is that with converted FFAs?
This is Joe. I guess I can take that. Sure, that's the traditional way. The normal way would be checking your free fatty acid content, and so that is the typical way of measuring the efficiency of the reaction and when it's complete.
We've got another ethanol question. Joe, Tony, or John, do you have any information on whether any ethanol plants have minimized or decreased their phytase dose when using MSA?
This is Tony. I can take that one. No, because we only have one application right now where we're actually acidifying beer feed. So that's something we would like to test down the road, but we just haven't had enough time for that specific application yet.
Okay, thanks. And just we've gotten several questions over the last hour about the broadcast being made available. It is being recorded, and within a matter of a day or two, perhaps by Monday at the latest, the broadcast will be available on our website, biodieselmagazine.com. And if you go up to the top and click events and then click webinars, if you're registered for this event, you'll certainly be able to access the recording once we get it posted to our website. Let me see another question. This question specifically for John. John, won't dropping the pH to below 4 eat the scroll in your tricanter?
We did not have that issue in particular. Now again, we being a front-end process, our temperature is a little hotter than a back-end process. We also have a little bit less solids going to it, so we have not had that issue yet.
For Benjamin or Joe, how about the application of MSA? It wasn't clear by the question, MSA or MSA-XP, for specialty esters, namely esters of long-chain alcohols and oligomerization of esters.
Joe, I know you worked with Dennis on this one before. Do you mind taking this one?
Sure. No, not at all. It's certainly MSA. MSA is used for a lot of different applications and chemical reactions and different types of esterification, and so any reaction such as the one that was discussed, I think formation of estolides, etc., is what maybe the commenter is, or the person who asked the question is considering. That it is possible to use MSA for that because it's a strong acid catalyst.
Okay, thanks, Joe. Let me see here. We got more questions coming in. For the ethanol team, did you look at emulsion between starch, oil, and protein? Usually starch will wrap around oil and protein will stabilize it. If oil extraction is done after liquidation and partially treated with GA, might be a better yield.
This is Tony. No, we haven't looked at that. Specifically, that question is probably for the front end. We did the laboratory studies that John reviewed, and then went straight to the field study.
Okay, thanks, Tony. A biodiesel question is MSA. Again, it's not specific. Is MSA or MSAXP soluble in methanol and biodiesel? What amount is required as a catalyst, and how is it removed after the reaction?
I'll take that. So this is Joe. So MSA is very soluble in methanol. It would be sparingly soluble in in biodiesel, if at all. I mean, it just would be very, very, very low level. But if given the opportunity, it will basically be move into the water or methanol phase. So I believe that was part of the question, and the other part was like what concentration you would have to use it depends a lot on the free fatty acid level, for example. I mean, if you're talking about a free fatty acid level that's in that 10% range, then you would probably, you could certainly consider using around 0.3 weight % of active MSA to the the free fatty acid, or to the oil with free fatty acid that you're trying to esterify. For higher amounts of free fatty acid, you probably would use more catalysts. A good point to be made in general about MSA, say, versus sulfuric acid, is that it is much better, it works a lot better with high levels of free fatty acid. So you can get good clean reactions with palm fatty acid distillate, which is close to 100% free fatty acid with MSA, whereas with sulfuric acid, because of all the side reactions, it really can cause a lot of problems downstream.
Thanks, Joe.
You're welcome.
There's a question here. Can you please elaborate on how MSA decreases corrosion inhibitor usage? Joe or Benjamin?
Yeah, Joe, I think that's
yeah, okay. I'm not so sure that I could say that so with this, I'm assuming this is a biodiesel question, and so typically, we are not talking about adding a corrosion inhibitor in a biodiesel esterification reaction. So I don't know of any cases where you have to do that. So I guess I can't comment on that. So maybe if the person who asked the question could clarify, Ron, we could potentially address it a little bit better.
Okay, if the person who submitted that question would clarify or follow up on that, would certainly appreciate that, and we'll try to address it again. What quantitative ranges of water content are acceptable for efficient Lutropur conversion to biodiesel?
Can you repeat it one more time?
Yep. What quantitative ranges of water content are acceptable for efficient Lutropur conversion to biodiesel?
Okay, so that's basically, I can give you a general answer, and that is that the greater the water concentration, of course, the slower the reaction is going to occur. And in Ben's presentation, he had an example where even a small amount of water that comes in with the acid itself, say in the case of Lutropur MSA, which has 30% of it is water, compared to Lutropur MSA XP, where only there's 6% water, you can see a clear difference in conversion. So in general, water is a natural byproduct, of course, of the esterification reaction, and as it is formed, the reaction does slow down. And typically for reactions that are that have a lot of free fatty acid, those would be done in 2 steps. So you would bring the fatty acid levels down from a high level to a lower level, and take that material, isolate it, and do a second esterification.
All right, thanks again, Joe. A few more biodiesel related questions. And this is more of a general question, and I think Benjamin had gone over this in his presentation. But in the neutralization processes, can Lutropur MSA XP improve reaction and/or separation time?
I mean, we've seen evidence that the MSA 70% showed better separation from neutralization. Like I said, we've really focused on the esterification of free fatty acids when it comes to testing for the XP. So I, haven't actually seen data for the neutralization, but I would, Joe, you can jump in here if you want, but I would assume that since we saw that the 70% showed better separation, that we would also see that for the neutralization. Absolutely.
I mean, there's the purity of Lutropur MSA and Lutropur MSA XP is the same. I mean, the main difference is the amount of water, and then, as Ben pointed out, there are other advantages in conversion and lower corrosivity, but for performance in other parts of the process, you would have to use, on a weight basis, less of Lutropur MSA XP because it's higher concentration, but it would still perform, I would expect, exactly the same way and have the same benefits that Lutropur MSA has.
Does BASF recommend the addition of water when conducting triglyceride esterification?
I'll let you have that one, Joe.
Okay, so at the triglyceride, typically, if you're doing an esterification, you have to have a fatty acid present. So if it's a true triglyceride and very low free fatty acid, there would be no need to add water. So I guess I would say there would be no need to have water in that case, typically. Water in general for an esterification reaction would not be a good thing. Okay, that's just in general.
To this point, have you had any success or experience replacing sulfuric acid with Lutropur MSA XP? It is a relatively new product to the industry, but if Benjamin or Joe could address that.
I'll take that one. It's too new at this point. Like I said in my presentation, I mean, we just, or the first batch of it was made back in October. So that's, exactly the reason why we're doing this webinar. It's why we've been doing advertisements, things like that. So no, it's on the way, but we haven't hit there yet.
Then perhaps would be a similar question. Are there any cases of industrial application of Lutropur MSA XP in biodiesel production plants using soap stock as raw material?
No, not yet. But certainly, there are. We do know customers are using regular Lutropur MSA, the 70% version that we've been selling for some time for that application. And again, it would work in the same fashion, certainly as the Lutropur MSA.
Okay, I'm getting questions in now live, so I'm just going through them to make sure. Okay, in a biodiesel free fatty acid esterification using a low dose in that 10% range, what are the recovery operations? Does it stay with the methanol perhaps? Any effects on methanol distillation?
So yeah, it would. This is Joe. Yes, it would stay with the methanol. I mean, in a lot of ways, you're going to see similar from a processing standpoint. You would go through the same processing steps that you would with sulfuric acid. The big difference would be that with sulfuric acid, a lot of times there can be a longer separation time between your oil phase and your water methanol phase. And with MSA, you would see much faster, at least that's been field experience and certainly our lab experience, you see much faster separation of oil and water phase. So in general, the experience is that our customers have seen is that operations are smoother with the use of MSA versus sulfuric acid because of that quicker phase separation. Certainly that would be the case with Lutropur MSA XP.
Okay, thanks, Joe. Probably be a question for Benjamin about your presentation. In the biodiesel presentation, what is the amount of water in the comparative test between Lutropur MSA XP and Lutropur MSA on 316 and 304 stainless steel?
So I'd have to go back and double check just to make sure, but I believe the slide they're talking about would be at the actual provided water content. So I think if this was the one where it was 14 days worth of corrosion at, what was it, 140 degrees, I think that was just the acids as they would show up. That's why the second one, after that, we showed it at actual biodiesel production levels, or biodiesel condition.
Okay. We've got another question here. Oh, I'm sorry. Go ahead.
And I hope that answers it. I hope I'm thinking of the right slide.
Okay. Is there an ideal pH for best separation of esterified oil and residual water and MSA?
That's a Joe question.
Okay.
Ron, would you repeat the question for me?
Sure. Is there an ideal pH for best separation of esterified oil and residual water and MSA?
Not that I am aware of that. Whatever the catalyst is basically the MSA catalyst is basically in the water phase. So it's whatever that happens to be based on the amount of acid that you've used for your esterification, but I'm unaware of a specific pH requirement or optimal one, at least to my knowledge.
For biodiesel and estolides, who do we contact for more detailed discussions?
If you wanna have more detailed discussions, you can definitely reach out to me. I believe my contact info will be provided to everybody, right, Ron? You can definitely get a hold of me. We can talk more about getting connected with Joe potentially if we need to have that type of discussion, or if you just want to talk commercial terms, we can go over that as well.
We've got let me see here, we've got a couple of more questions that we're going to get to. Most of them are biodiesel related. Bear with me for 1 second. So here's a question. Now you can answer it or not. For example, with soap stock with 32% fatty acids, 28% impurities, and 40% humidity, how would you do acidulation or even directly the esterification of triglycerides and FFA into biodiesel? I can repeat that if necessary.
Yeah, would you please, and we might have to answer that one offline and ask the,
okay.
But go ahead and repeat it again.
Absolutely. For example, with soap stock with 32% fatty acids, 28% impurities, and 40% humidity, how would you do acidulation or even directly the esterification of triglycerides and free fatty acids into biodiesel?
I would like to, I would prefer to have someone, if they wouldn't mind, to contact Ben, and we could arrange a discussion, because that's a little more detailed than I think I could probably do justice to that question at this point. Okay,
sure. We're getting close on time here, but so this is kind of a general question, but if Joe or Benjamin, you'd like to address it. Using MSA XP in the first step of biodiesel production, which is the esterification of free fatty acids contained in cooking oil, what are the specific steps and specific conditions to be used? Offline?
Well, you know, I could say in general, we're really not talking about something so different from what a customer might be doing with sulfuric acid, and I think that's a real problem. Is that every process, every feedstock is different and requires some different conditions and maybe different levels of catalyst. So if the customer is, the person asking the question is using sulfuric acid right now, one good way to start is to start at the same level, although we have seen that MSA can be used often at lower levels. And certainly, you know, I would encourage the person asking the question to reach out to Ben if they would like to have a more detailed discussion.
Thanks, Joe. I want to thank our panelists once again. You know, and anybody who has a question that they want specific answers to that either we haven't addressed or you'd like to follow up on, I definitely encourage you to reach out to Benjamin Plants and Joseph Borst at BASF, as well as Tony Newton, and then John Brasher with Ergon Biofuels. That's all the time we're going to have for questions. At this time, I'd like to once again thank the panelists, and a special thank you to our sponsor, BASF. And finally, we're going to tell you about a speaking opportunity for those of you who might be interested, and an exclusive discount for those of you who are joining us today.
Great, thanks, Ron. One upcoming event that we believe is of interest to everyone on today's webinar is the National Advanced Biofuels Conference and Expo, and that's taking place June 19th through the 21st in Minneapolis, Minnesota. And if you're interested in speaking, the abstract period is currently open, so it's a great way to get your name out, get your products, your services, any of the innovations that you're looking to promote. It's a great way to do it. So we would urge you to submit an abstract. There's the deadline. You can go to advancedbiofuelsconference.com to submit. We've got a few different titles here of what we're looking for, but primarily there are 2 tracks associated with this event, and it is the advanced and cellulosic ethanol track, and then a biodiesel and and other advanced biofuels track. So there is a cellulosic side and then a biodiesel side that we're really pushing with this event. And again, this is co-located with the world's largest, longest-running ethanol conference, the FEW, and it's now in its 33rd year. And we always have great turnouts in Minneapolis. So I would definitely urge you to submit an abstract if it is of interest to you. If you're looking just to attend, we do have an exclusive discount. You can receive a $250 discount on your full conference registration. When you go online to register, just use the discount code WEBINAR, and you can take advantage of that. And our deadline for that is May 10th. So again, check it out on the website, see if it is of interest, and we hope you take advantage of that. On behalf of Biodiesel Magazine, and Ethanol Producer Magazine and BBI International, we'd like to thank you for being on today's webinar. And hopefully we'll be in touch in the future. Have a wonderful afternoon.